Welcome to this lecture on the core concepts of machine learning models, presented by Dr. Microlearning in December 2025. Over the next few minutes, we'll walk through the essential ideas that drive practical model design and deployment, from basic terminology to advanced architectures and lifecycle practices, so you can connect high-level concepts to everyday model decisions. In this slide, we clarify the model stack by separating the algorithm, the hypothesis, and the final model. Think of the algorithm as the training procedure, the hypothesis as a candidate function you're testing, and the model as the selected, tuned function you deploy. Understanding this flow helps prevent confusion when selecting methods or debugging pipelines, which the diagram illustrates clearly. Supervised learning aims to learn a mapping from input data to labels by minimizing prediction error on labeled pairs. Typical algorithms include linear regression for continuous targets, decision trees for rule-based splits, support vector machines for boundaries, and gradient boosting for high-performance ensembles. The gauge graphic highlights typical enterprise accuracy on tabular benchmarks, showing performance expectations and trade-offs to consider. Unsupervised methods reveal structure without labels and are useful when ground truth is absent. Clustering groups similar points, think k-means for segments dimensionality reduction like PCA, simplifies complex features for visualization or compression, while density estimation such as dbScan uncovers underlying distributions for anomaly detection. The visuals show clusters, a funnel to lower dimensions, and contour maps to emphasize these roles. Here we contrast reinforcement learning and semi-supervised learning. Reinforcement learning optimizes sequential decisions through an agent interacting with an environment, learning from state transitions and rewards, which suits robotics and supply chain control. Semi-supervised learning mixes scarce labeled data with abundant unlabeled examples to boost performance in tasks like speech recognition and bioinformatics, leveraging mixed data to reduce labeling effort. This slide focuses on transformers and why they dominate NLP and multimodal tasks. Their self-attention mechanism captures long-range dependencies in input sequences, enabling strong few-shot adaptation, and the slide calls out near state-of-the-art contextual accuracy. Enterprises are adopting transformers broadly, and the visuals illustrate performance metrics, the attention block, and the rising impact across business applications. We compare graph neural networks and gradient-boosted decision trees as complementary tools. GNNs excel on relational data for tasks like fraud detection and recommendations, delivering high precision and recall as shown by the F1 score callout. GBDTs remain the top choice for tabular forecasting thanks to interpretability, handling heterogeneous features, and requiring minimal tuning for efficient deployment, as the diagrams convey. This slide covers optimization and performance tuning fundamentals, starting with the bias variance trade-off and loss functions that guide learning. Stochastic gradient descent operates in an iterative mini-batch loop sample, compute gradient, update parameters, until convergence. Validation curves and diagnostics reveal overfitting or underfitting, and techniques like regularization, early stopping, and data augmentation help balance complexity and generalization. The final slide outlines the ML model lifecycle and compliance framework for sustained trust and performance. It emphasizes continuous monitoring, transparency, and drift detection. MLOP's practices like CI, CD, retraining, and monitoring for reliable operations, and exploring emerging techniques such as federated learning and explainable AI to meet 2025 compliance and privacy demands, while ensuring accountable, interpretable models.